At this point, I think I would like to make the connection between matrix multiplication, as you know and love from your linear algebra classes, and linear functions from RP to RQ a little bit more explicit, because the next section I'm going to want to say a few things about linear functions that you know, but you know them in matrix language, not in linear function language. And so I'd like to be able to pass easily from one to the other. So here is, it's not quite called a proposition in your book, but here's the start of section 6.4. We're going to spend most of this video in section 6.8. Let's let A be a function whose domain is RP and whose range is RQ. Be linear. Then, and let's say if we write elements of RP and RQ as column vectors, then there is a unique Q by P matrix M such that A of X, A, remember, is a linear function, is the matrix M times X. This is why people often write linear functions as just AX rather than A of X. We get lazy and leave the parentheses out. We're sort of identifying the linear function A with the matrix M. And of course, matrix multiplication, you don't need parentheses. And let's write out the proof of this thing. Let's let X be in RP. So X is equal to some column vector, which we can write as X1, X2, down to XP. And we can write it, this is X1 times the vector, which starts out with a 1 at the top, and then so on up to XP times the vector that's a bunch of zeros and a 1 at the bottom. And then remember, we've got a name for these vectors that have 1s and zeros. So X we can write as the sum from K equals 1 up to P of XK times EK, where EK is these unit vectors. So A of X, that's A of our sum, then because A is linear, we can take this up. We can move the sum out, and we can move the real numbers, the XKs, out. And now let's give A of X a name. Let Y equal A of X. Y is an element of RQ. So Y is, we can also write that as a column vector. Y1 through YQ. And now, how do we pick out one of the j's. Yj is the inner product of y with dj, where dj is a column vector, bunch of zeros, a 1, bunch more zeros, is the unit it's the standard basis vector. Now it's in RQ rather than RP. Remember the EKs, where EK is the standard basis vector. In RP now, not RQ. So we're using E and D because we've got these two vector spaces, RP and RQ, and we don't want to use the same letter for both of them. And then you see you can pick out the inner product. You can pick out the jth component of y by taking the inner product with dj. So we can write this as yj, that's the inner product of j with y, that's the inner product of dj with a of x, that's the inner product of dj with our sum, then because inner products are linear, we can move the xk out. And let's not forget our sum from k equals 1 to p here. You may recognize this as matrix multiplication, but in case you don't, let's write it this way. dj a of e1 x1 plus inner product dj a of e2 x2 up to dj a of ep xp. So we can see that the vector y1 down through yq, that's the matrix this matrix D1 A of E1 up through D1 A of EP DQ A of E1 through DQ A of EP X1 down through XP. So we've seen that we can indeed write any linear transformation as a matrix. Uniqueness is pretty quick. If A of X equals MX, then inner product of DJ with A of EK, that's the inner product of DJ with M times EK. That's going to be the jkth component of M. So M must be the matrix above. So A has indeed a unique matrix. So now let's recall some facts about invertible matrices. So let's let A be a linear function from Rp to Rq. So A of x equals mx. M is a Q by P matrix. And then we recall, hopefully this is a fact you all learned in your linear algebra class. If not, it's a useful exercise to work out why it has to be true. If P is less than Q, then A is not surjective. So in particular, it is not invertible. A matrix is invertible if it has a matrix inverse. A function is invertible if it has an inverse in the sense of invertible functions, if it's one-to-one and onto, so there's a function that undoes it. And you can see that multiplication by an invertible matrix is an invertible function, and the inverse in the sense of functions is multiplication by the inverse in the sense of matrices. And on the other hand, if P is bigger than Q, then A is not one-to-one. And so again, it's not invertible. And if P is equal to Q, we can check easily. Well, relatively easily. You can type it into a computer whether A is invertible by computing the determinant of M. Now, there's a whole theory of invertible linear transformations. This is a lot of what goes into a linear algebra class, but at this point, we're going to assume you know all that stuff, that you understand the extensive theory of invertible linear transformations, or at least that there is one. And now we are interested in invertible nonlinear. And in this chapter, but different, we're interested in invertible nonlinear differentiable functions. And remember, differentiable, for a function to be differentiable, that means it's got this linear function that shows up that's its derivative. So we might be able to exploit some of the linearity invertibility theory for linear functions by looking at the derivative of our invertible nonlinear function. So here is a lemma about invertible functions that are also differentiable. Let's let U be a subset of Rp, W be a subset of Rq, F is a function, and we'll suppose that both of them are open. And we're going to let F goes from U to W be invertible, and let be one-to invertible, meaning bijective. Let's say bijective. G is F inverse, set theoretic inverse. Now let's suppose that C is in U and F is differentiable at C. And G is differentiable at the point F of C. And the conclusion is that then the two linear functions df of C and dg of f of C, they are invertible, are also bijective. Also known as invertible linear transformations. And in particular, they are inverses to each other. df of C, that's a function, remember. Its inverse is dg of f of C. Now let's write out the proof of this. Let's let I be a function that goes from U to Rp, be given by I of x equals x. So I is the identity function restricted to U. We're going to say its domain is U, just like f. Then if x, so this is a perfectly good function, and I claim it's a differentiable function. In particular, it's differentiable at C. So if x is in U, then we're going to write I of x. This is also known as x Well, we can write down an I of C. So that's x equals c, and then I have to add to that x minus c. And I'm going to go ahead and put the identity function there. Let's call this the function with domain u. Let's put a subscript of u on it. And that because we want our because this second I of x minus c, I would really like I to be a linear operator, which means it's got to have a domain. Its domain has to be all the real numbers. And then if we're writing out the formula for differentiability, I need to put a norm of x minus c here times some continuous function that's 0 at c. Why don't I just put 0 there? That's 0 everywhere. So the derivative of the identity in u at the point c, that is equal to the identity function, where I is a linear function from Rp to Rp. It's still the identity function. The distinction I'm carefully making with this u subscript is, do I want the domain to be just the open set u, or am I allowing the domain u to be everything? Now, by theorem 6.5.13, G composed with F, because G and F are inverses, because G and F are both differentiable, this is differentiable at C. And I can write down a formula for the derivatives. The derivative of G composed with F at the point C, that is equal to the derivative of G at the point F of C. Because that's a linear operator, we compose it with the linear operator df of C. But we have that G composed with F is the identity, is our I sub u, is the identity in U. And by proposition 6.5.2, since U is open, this is why I needed U to be open, we have that the derivative of I sub u at C is unique. There is at most one linear function that can be the derivative of I sub u, that can be the derivative of G composed with F. So the identity operator, is the derivative of the identity operator at C. Yes, the derivative of the identity operator is now the identity operator is itself. I realize this seems somewhat strange. You're used to the derivative of x being 1, but that's just how derivatives of identities work. This is the derivative of G composed with F at the same point, because the I sub u and G composed with F are the same function. And so we can write the identity is the composition of DG and DF. You may recall that it is possible to have non-square matrices whose product is nonetheless the identity. For example, if we multiply 3, 1, negative 7, negative 3, negative 1, 8 by this matrix 4, 3, 2, then 3, negative 2, 1. If you multiply that out, you can check and see that that indeed comes out to the identity matrix you know and love. And of course, those aren't invertible linear transformations, so we aren't quite done. Let's go ahead and name and rename this identity to I sub p. That's just to emphasize that it's the identity in p dimensions. It represents multiplication by the p by p identity matrix. And then we can observe that then we can make a very similar argument to see that I sub q, the q by q identity matrix, is df of g of f of c, which is just the same as df of c, composed with dg of f of c. So df of c and dg at f of c are both invertible. And I'll mention a corollary, which is that Q is necessarily equal to P. That is, if U is a subset of RP, W is a subset of RQ, F goes from U to W, and there is a C in U such that F is differentiable at C, and F inverse is differentiable at F of C, then P and Q have to be the same number. So if you're looking for invertible functions, they have to be going from spaces of the same dimension, at least if they're going to be differentiable invertible functions. That's not always true. There are bijective functions from, say, R to R2, but they aren't continuous, let alone differentiable. So if you're looking for a nice invertible function, one that at least it's differentiable and so is its inverse, then you've got to be looking at a function that goes from sets of the same. So let's summarize what we've just seen. We've just seen that if U and W are open subsets of RP, let's let f be a function from u to w be differentiable. And we've seen that if f is invertible, so it's one-to-one and surjective from u to w, and being a bijection, it has an inverse. If the inverse it is also differentiable, then we can conclude that the derivatives df of c is an invertible as a linear transformation. Question: do we need to check this part? So if all we have, if f is just differentiable and invertible, then is f inverse necessarily differentiable? Is it even continuous? You saw on the last exam possibly that if you can extend f to an invertible function on a compact set, for example, if the closure of U is compact, and f is continuous and one-to-one on the closure of U, then f of closure U is compact and f inverse from closure U from f of closure U back to the closure U is continuous. As it turns out, if you're interested in differentiability, you don't even need to go to multi-dimensional case to get a counterexample to this one. If you let f of x be, say, x cubed, f is bijective and invertible, but f inverse, that's the cube root of x, is not bijective and, differentiable. But the inverse is not differentiable at c at 0. So when we're going back to this question, we need to add another condition to it. We need df of c. We need the derivative to also be invertible. If that is not true, well, we know that if f and f inverse are both invertible, then df has to also, are both differentiable, then df has to also be invertible. So certainly we need f to be f and df to both be invertible in order to hope to have f inverse be differentiable. So what if so we've seen that to have the inverse be differentiable, we need the derivative to be invertible. what if that's all we have? If f is differentiable, and the derivative is invertible, is f invertible? F inverse differentiable? If so, that is, if so, is its inverse also differentiable? So let's have two examples of weird behavior. Here is the first one. Let's let f maps from, you can go from all of R2 to all of R2, be given by f of x1, x2. That's going to be, let's say, e to the x2 times the cosine of x1, and then e to the x2 times the sine of x1. And then your matrix, remember our derivative, it's the matrix of the partial derivatives, the matrix partial j f sub k. That comes out to this matrix, minus e to the x2 sine x1, then e to the x2 cosine x1, e to the x2 cosine x1, e to the x2 sine x1. That, if you want to see if it's invertible, you compute its determinant. And the determinant comes out to minus e to the 2x2. And then, or rather, e to the 2x2 minus sine squared x1 minus cosine squared x1, which is minus e to the 2x2, is never 0. So, and this matrix is always continuous, so we know that df of x1, x2, it's always given by multiplication by this matrix, and that is always invertible. But let me go ahead and draw some pictures for you. Let's say you start out with this rectangle. Let's say it goes from 0 to 1 here, or rather, your vertical coordinates are 0 and 1. Your horizontal coordinates can be pi, and then negative pi 0, and up here negative pi 1. If you think about what this does, what your function f does to this thing, what it does is it sends it to a half circle, and that is bijective. You take a strip that's twice as wide, Sorry, these all need to be pi over 2. That goes to this entire big annular region. Either missing or double counting this line here. And then if you take a very long strip as your domain, what that maps to, that's still going to map to the circle, or rather to the annulus, but it's going to double count. The middle region will map to this side of it. And then this part here, you'll get, in fact, you'll double count here, this part here. You'll double count here. So you'll see this is no longer 1-to-1. So we have that even if the derivative we can fail to be bijective. On large domains, you'll remember on the small rectangle up near the top, we were bijective, and it turns out that if your derivative is invertible, the function has to be invertible on all small enough domains. Here's another example I would like you to keep in mind. This example is a one-dimensional example. Let's let f of x, it's a piecewise defined function. It's 0 at 0. And let's take x over 2, and then we'll add to that x squared cosine of pi over x. Otherwise. And then by example 2.4.4, f prime of 0 is 1/2. That is invertible. The derivative is the linear transformation multiplied by 1/2 that is invertible. But the problem is, if you actually zoom in on the graph of this thing, and I encourage you all to do it on Desmos, you'll see a bunch of little tiny peaks zigzagging up and down. So you'll see in particular, f is not invertible. In any neighborhood of 0. No matter how much you zoom in, you get these little peaks, and near a little peak, you're not to 1. You're not 1-to-1. I'm going to finish this video by stating the inverse function theorem. This is sort of the big theorem that's the point of section 6.8 that we're going to be proving. And you may notice some of the finicky details. You may notice us avoiding our previous examples. So we're going to be proving this over the next few lectures. So let's let X be an open subset of Rp. And we're going to take a function that goes from X to Rp. Remember, to be invertible and continuous, you really need to go from Rp to Rp. So let's assume that f is continuously differentiable. And I will tell you what that means at the start of the next video. And let's let C be a point in our domain. And we're going to suppose that the linear transformation that is df of C is invertible. And then the conclusion is that there is an open set U that's contained in X with C in U such that F is 1-to-1 on U and let's list this as a bullet point. U is open. So we've got an open set where F is bijective. It's 1-to-1 on U, so and it's onto its image F of U. It's certainly it's injective on U, so it's bijective U to F of U. Turns out that you can require that F of U is also open, and F inverse, that's a function from F of U back to U, is continuously differentiable. And then we can also notice that by our lemma up above, df of C inverse is equal to d f inverse of f of C. And that's what we're going to be proving in the next several videos.